move on to the next talk from Emma Hossain from UMBC on the time series classification.
Introduction.
What?
I'll introduce.
Yeah, okay, sure.
Thank you. I'll be talking about work on time series classification of supraglacial lakes. Again, this is another really fun collaborative project led by Emam from UMBC, Osman, who work on the time series classification, and Devon, whom I'm representing today, who was a postdoc in iHARP, who's currently at KU Leuven. Ali, another collaborator of ours, is online, and Hammad was a high school student mentored by Devon, and Brendan is an undergrad. So I'll give a quick introduction, and Emam will talk on the time series classification. As Vandana mentioned, and Zichi as well presented really well, the mass loss in the Greenland ice sheet has a big impact, not only locally, but also on the global sea level and global climate. Currently, we are losing about 13% of the net mass from the ice sheet. And this meltwater runoff is one of the dominating factors in terms of the ice sheet mass loss. So in terms of what happens for the meltwater runoff, during summer, ice starts melting, creating these supraglacial lakes on the surface. And some of them melt and drain out, some of them refreeze. So what we are looking at is how do these different supraglacial lakes behave over a season, especially over 2 years, is what Devon looked at, and we're looking at different time series classification algorithms. So just quickly, how we identify this. So there are, we use optical images from Sentinel-2 and Landsat-8 to create a time series of the seasonal evolution of these lakes. So that's a optical image of a lake as it melts over summer, June, July, and then starts refreezing as winter comes. So in this case, you see this melting over the season, and then it quickly refreezes. So we can, so we identify the boundary of the lake and then plot the amount of water as a fraction, a percentage of water, which it fills up to 100% and then refreezes, so goes back to 0% when the whole lake surface is frozen. But then we can also look at microwave imagery from Sentinel-1, and microwave is absorbed by liquid water. So even if the surface freezes, if there is liquid water below the frozen surface, you can see that with microwave, whereas the optical image will not be able to see that. So what's plotted here in the red line is the backscatter anomaly of microwave. So as water forms, the microwave is absorbed, so you have lesser microwave backscatter. So you can identify buried lakes with this microwave imagery from the satellite. So using this, we identify 4 different types of supraglacial lake behaviors. One of them is the refreeze, which we just saw, that you form the lake and it suddenly refreezes. Another one is where the surface refreezes. So you see that in the optical image in the greenish blue line, whereas the red line, the microwave, you still see the liquid waters persisting after the refreeze of the lake. So that's a buried lake. How do I? Okay, thanks. Oh, okay. Yeah, the mouse was on the video, I think. So that's a buried lake. Another one is rapid drain, where you get this melt and then the lake drains. So you see the liquid water drain out of the lake. And the fourth one, it's going. Yeah, and then the fourth one is a slow drain lake, where you see this melt and then the liquid water persists for a long time until the deep winter time. So that's a slow drain behavior. So we have these 4 different types of lakes: refreeze, buried, rapid drain, and slow drain. And now Emam will talk about the time series classification.
All right. So we are talking about time series classification. So what's time series classification? It's a machine learning task where the goal is to label different data points collected over time. And these are sequential data. So we have times data collected over different points where each point is dependent on the previous data points. And the difference between traditional classification and time series classification is that uh, in this time series classification, data points are timely dependent, so they have temporal relationships. But in traditional classification, the data points are independent and they don't have any temporal relationships among them. So there are several time series classifiers in machine learning and deep learning techniques. So based on decision trees, random forests, k nearest neighbors, and also from deep learning, they have long short-term memory and combining FCN, fully connected layers. So there are some existing deep learning and machine learning techniques, but they have some issues that we are going to discuss next. So the data set we considered here is the Greenland ice sheet data set, and we collected daily interval time series data over 2 years, 2018 and 2019. And we have two features here. We can see that backscatter difference on the top and the water percentage. As Dr. Subramanian already mentioned, like what are those and how we calculated this water percentage and backscatter differences. So we have considered the data from May 1st to December 31st. As we can see that for the first 4 or 5 months, there is nothing really happening. So we didn't consider when we train these models. So the performance that on the Greenland ice sheet, we already mentioned some time series classification techniques, and we see the performance of these machine learning and deep learning classifiers on the Greenland ice sheet dataset. As you can see that the blue line here shows the performance only on the backscatter differences, and the yellow line shows the performance on the backscatter difference and water percentage both. If you see the trend here, obviously adding the water percentage improves the model, although they only achieve like up to 86 and 87% accuracy. The best model achieves 86 and 87% accuracy. But the problem of this machine learning and deep learning classifier is that they are computationally inefficient, and they also need more and more data to train them efficiently. So what we propose here is a new technique based on reconstructed phase space, where we get rid of the temporal connection that we have in the data, and we embed the time series and then construct a phase space which does not have any data temporal relationship among the data points. So we have a time series of okay. So we have a time series of x1, x2, xn, and we use time delay embedding to create a delay matrix using time delay and embedding dimension, two features that we are going to use as a grid search to find the optimal features. And if you consider the sine wave of the time series of the sine wave for timestamp 0 to 4 pi, you can see that RPS has no time dependency in the reconstructed phase space. So that's what we are trying to do. And we use Gaussian mixture models, which is a probabilistic model, which mainly used in clustering and classification. And it can have up to M mixtures. So in this case, we use 10 mixtures for our lake classification. And each lake is represented by one Gaussian mixture model, which is trained only one representative sample of each class. So, for example, this is the GMM model for Irish dataset, which is a famous machine learning dataset used for classification techniques. And you can see that each cluster has their own, each class has their own cluster, and we can use this cluster for classification technique. So we trained different GMM models. First, we only use backscatter differences. So you can see that from May to the end of the year, we have these backscatter signals that we have. And the reconstructed phase space shows something like this. We use grid search, and from the grid search, we found that optimal time delay is 13 and dimension is 15. As we cannot show 15 dimension, we only showed first 3 dimension of the reconstructed phase space. And this is what it looks like for all four different classes. And the accuracy that we got for the first model is around 58%. And you can see that there is a huge misunderstanding between the drain and drain slow events. So we thought, okay, what if we combine these drain events together? And you can see that the performance improved like more than 85%, and drain events are more identified more accurately. As we saw in the deep learning and machine learning models, using water percentage with backscatter signals improve the performance, and that's why we considered both for the new GMM models. And this is the new RPS for considering both backscatter and water percentage. Again, we found a time delay of 11 and dimension of 9 as the optimal parameters. And this is the results that we got with drain and drain slow separated. And previously it was 57%. Now it increased up to almost 61%. And also the 85% of previous drainage events, 85% of the previous case, we also achieved around 90% accuracy for the drain events combined techniques. So the fascinating thing here is that we achieved this accuracy, almost 90% accuracy, using only one sample per class. So instead of machine learning models where you need thousands of samples to train a model, we only use 4 samples for 4 class, and we achieved 90% accuracy. And so we also noticed that there is a greater percentage of lakes drainage during the warmer melt year than during a colder year. And our 2-year dataset provides an additional insight to dynamic factors that may control supraglacial lake hydrofracture events. And as I mentioned, only one sample used for training the model, which is very significant, and also incorporating the water percentage with the backscatter anomaly improve the performance of the model. So in future, we are already working on some modifications of the model. So we are using multiple representative sample because we need to notice that there are multiple patterns in the same class. So we are using multiple samples from multiple patterns of the same class. And then we will use majority voting techniques to find the maximum likelihood of the model. And also we already submitted a journal paper where we use a different machine learning technique based on rocket classifier, but it involves some post-processing techniques. So we are trying to build this classifier so that we don't need domain-specific post-processing techniques anymore. Thank you so much. If you have any questions.
I really enjoyed your presentation. I have like 100 questions, but it would just show the things I don't understand and take too much time. I was curious about your question or your point when you said that your model was hungry for data. Are you generating, it looked like you're generating a lot of your own data, right? From the images. Are there other sources that you can use to run your model on? Or?
So we are collecting data directly from Sentinel-1 and Sentinel-2 satellites, but we can also use data augmentation techniques like we use in machine learning. I'm a machine learning person, but data collection and data pre-processing is mostly domain science. Dr. Subramanian and Dr. Dunmire. They work mostly with the domain science data, but we can generate more data using machine learning techniques like data augmentation, different type of data augmentation technique. But data hungry, yes, machine learning models are data hungry. Even if you augment data and feed more data, they might still need more data to identify significant changes or small details. Like as we saw, drain and drain slope, very hard to identify. Like drain and drain slope both are draining, but one is rapid drain and one is slower drain. So how do you differentiate between these two? So this kind of techniques may hinder the performance of the machine learning models, even if you feed more and more data.
Could I ask a follow-up? Just a quick. So if I understand though, there's not a lot of data available for you to reuse. You've got to create your own sets,
yes,
basically.
So far, yes. So far we only have data for 2 years. Yes. Thank you.
So what is the scale of the size of the lakes that you're looking at? Looking at the screen here, are you looking at tens of meters? I mean, are you looking at small lakes and large lakes, or only very large lakes?
Sorry, I didn't get it.
I mean, when I look at this picture here, your scale is, you're showing small lakes. Is your work applicable only to very large lakes, or applies to even smaller lakes, the one that you're showing on the screen here?
It should be applicable to smaller and bigger, both of the lakes. Yeah.
So the data set that you have at resolutions of tens of meters.
Yes, so we have different types of lakes, smaller and bigger. They have different lengths of, like the lake has different lengths. So we can identify both smaller lakes and bigger lakes as well.
Very good. Thank you.
Thank you.
Have to move.